Platooning is one of the key use cases for vehicle-to-vehicle communication which aims to improve traffic efficiency. In a platoon, the first car, the platoon leader, sets the driving velocity and all platoon members will follow it. Platooning cars constantly exchange platooning beacons, containing position, speed and acceleration data via their communication interfaces. This data is fed into a cooperative adaptive cruise control algorithm where it is combined with local sensor data. The controller then adapts the velocity of the vehicle to keep a constant gap to its predecessor. In a platoon, this gap can be much smaller than what would be considered safe for human drivers and even for state-of-the-art non-cooperative adaptive cruise controllers. This can be done because all members of the platoon are continuously informed about planned maneuvers. This way, braking, and even emergency braking, can still be done in a coordinated, safe way. However, this is only the case if all platoon members function properly and have good intentions. To secure the platoon against attacks, the radio communication can be secured using cryptographic signature schemes. While signatures can ensure integrity of the messages, certificates ensure the authorization of their senders. However, cryptographic means cannot ensure the semantical correctness of the message's content. The signature for a message containing wrong speed values is still valid. An attacker injecting forged data in its signed messages is able to cause crashes. In this attack, the attacker sends false speed data. This causes the victim to brake harshly, which provokes a rear-end collision. To detect and mitigate injection attacks like this, additional means for security are required. Misbehavior, or the transmission of false data, whether malicious or by error, can be detected with TriP, short for trust in platoons. In TriP, trust is modeled by using outcomes of past interactions to predict the outcome of future interactions and building up a reputation. Platoon members interact with each other by exchanging beacons, including position, speed and acceleration data. The receiver of a beacon determines the outcome of the interaction by calculating a so-called trust sample. Therefore, it compares the received data from the predecessor to its perception with its own senses, for example radar, considering multiple criteria. It determines how well the car matches the leader velocity. Additionally, it judges how accurate the reported position is, compared to its own localization and distance measurements towards the sender. Also, relative acceleration is considered. It should be nearly zero when CACC performs as expected but can be induced by forwarding false data to the CACC algorithm. Furthermore, also the jerkiness of the car in front is included in trust samples. Finally, if a car fails to send its beacons, or, so to say, expected interactions were not performed, it is considered as bad outcome. These trust samples are then aggregated in a Bayesian statistical model, called Dirichlet reputation system. Here, trust for a car is represented as a probability distribution. With this system, trust can evolve with new outcomes, keeping the history of previous interactions in mind. Furthermore, the reliability and certainty of trust can be judged by the standard deviation, as more and more interactions narrow down the distribution. To determine the current trustworthiness of a car, the expected value of the distribution is used. The trustworthiness of the car is also used in the aggregation process. Here, low trustworthiness lays more weight on the distribution, and less weight on the outcome of the last interaction, when aggregating both. Good trustworthiness, however, lays more weight on the recent outcome and less on the past. This way, trust will degrade fast within a few bad interactions, while building up trust takes many good ones. TriP is deployed on top of the controller and is fed with platooning beacons and sensor data, building up the reputation database. Misbehavior can then be identified by periodically evaluating trust for platoon members. As the detailed evaluation in a simulation study showed, TriP can reliably detect a variety of attacks against multiple control algorithms. In case an attacker is identified, a mitigation strategy has to be deployed. As demonstrated, misbehavior can have devastating effects on the direct victim, but also on the cars following. The cooperative mitigation strategy, proposed in the paper Securing CACC, also keeps the followers of the victim in mind. Therefore, the platoon beacons were extended to include the suspiciousness for the direct platoon predecessor. In other words, each car announces how probable an attack by the car in front is. When the misbehavior detection system of a car identifies an attack and the suspiciousness its beacons rises, the misbehavior mitigation follows these steps. The direct victim switches to ACC, which is independent of the beacons of the attacking car, but unstable when driving with the given CACC gap. Hence, the victim builds up a larger safety gap towards the attacker, which is required by ACC. Furthermore, the followers of the victim react to the suspiciousness by replacing their old platoon leader with the victim, effectively splitting off a new platoon behind the attacker. This way, the old platoon as well as the new platoon remain stable and safe, mitigating the attack. In this demonstration, TriP and the mitigation strategy can be seen in action. Again, the attacker will inject false speed data in its beacons, but this time, detection and mitigation are activated. When the attack starts, the trust in the attacker degrades. After the misbehavior threshold is exceeded, the victim will deploy its mitigation strategy. It switches to ACC and increases its safety gap towards the attacker. When the safe following distance is reached, it operates as platoon leader. The follower of the victim continuously monitors the suspiciousness in the received platooning beacons. When the suspiciousness is high and an attack is probable, it anticipates the deployment mitigation strategy by the victim and exchanges its old platoon leader with the victim. When the new platoon leader slows down to increase its safety gap, also its followers will do so in a stable way, avoiding the attack and keeping CACC secure.